So with this brief, I request Professor Manfred to start the webinar. Thank you.
Yeah, thank you very much for this very kind introduction. I hope you can see and hear me well. Otherwise, let me know. It is a pleasure for me to give you a talk on the Arctic climate system. That is a topic which we deal with now for a couple of years, and we do so by generous funding from our German Science Foundation within a project which is called Arctic Amplification. And then there's also some more explanation here. You can see that. It's called AC3, and it's a collaborative research center. And there are several German universities are involved, from Leipzig, Bremen, and Cologne. But there are also non-university institutes included in this effort. Alfred Wegener Institute in Bremerhaven, and Potsdam and Tropos here in Leipzig. So that means we work on this broad topic, and that's why I can show you a little bit, give you a little bit of an overview, and also a little bit of science, although I will keep that limited a little bit. Okay, so thanks again for this invitation to give this seminar, and I would now like to start. I have more or less 5 points that I want to cover. I'm not sure if I will be able to show all the slides, because it might take a little longer. Please interrupt me whenever you have a question, and also tell me when you are tired and when you would like me to stop. I can stop in the middle if you like. So I will give you a short introduction, fascinating Arctic, then a little bit about history of Arctic research and expeditions. Then I will show you some examples of changes that are ongoing in the Arctic right now. Then I will talk a little bit about processes and give you a summary. So let me start with the kind of fascinating Arctic topic. So why study the Arctic climate system? That's far away, and why should we go there? It's cold, and it's not like in the tropics where you have nice weather. So it's hard to observe things there. So there are certain things which make it worthwhile going there. It's a hot place in a sense. It's warming very fast, and it's warming faster than the rest of the world. I will show that in a minute, a little more detailed. It's very exciting to work there. So you see nature there. Here you see the polar light, for instance, and I always enjoy going there and take measurements. It's really exciting and tough, although it's tough. It, of course, plays an important role. It's a heat sink in the global climate system, and it's in the midst of rapid changes that may have climate impacts also affecting the mid-latitudes and even India and the whole climate, the whole globe. So that's why we need to have a look there. And another non-scientific point is that there's also growing economic and strategic importance of this region. And I will show you a couple of results why people are eager to know how climate evolves in the Arctic. One is accessibility of oil and natural gases. What you see here is a map of the Arctic. So in the middle is the North Pole, and you have Greenland here, and so on. North America, Russia. So you see where we are here. This is the Arctic Circle. And the blue regions, they show kind of a probability of the presence of undiscovered oil gas fields. Yeah, the darker the blue, the more high is the probability that there is gas or oil hidden. Yeah, and altogether, it is estimated that about 16% of the oil or 30% of natural gas are undiscovered there compared to the whole globe. So you can imagine if that's becoming ice-free, then people will go there and will, what they already do partly, and get these resources. Well, commercial shipping is another point. If you look at that slide, what you see here is, again, this is Greenland here, this is Europe. You see red and blue lines. Red lines are ship tracks of moderately ice-strengthened ships. So ships which can handle a little ice, I say. And the blue ones are the ordinary ships. And of course, if you transport goods from Europe to China, for instance, then it would be nice to go here this way, the northeast or the northwest passage, crossing the Arctic Ocean. And in the past, of course, you had to look for ice-free areas. This is for September here. In September, you could go here. So most of the ships could go this way, northeast passage. Huh? The red ones could make a shortcut, but not really changing. If you project that in the future, then what you see is that these ice-strengthened ships, in September, there will be no more ice here in September. So they can go straight through this through the Arctic Ocean to reach the Pacific. Yeah, and even the blue ones, there are much more ways, and here the Northwest Passage will be possible for them, which wasn't possible here. And that's a point which is important in terms of money and of tourism and commercial shipping. Okay, so high interest to go there, and to people want to know how that evolves. So people wanted to know that already in earlier times. That's why let me give you some slides about history. The first people, among the first people was John Franklin. He tried to find the Northwest Passage, just seen, but he ended up somewhere else. So he ended up in Greenland. So he failed, kind of, yeah. But that was already, almost 200 years ago, yeah. And there they didn't have good ships and so on. And it was really an adventure to do that. Amundsen is another important guy here in this regard. He successfly went through the Northwest Passage for the first time with a ship, which is shown here. Then the conquest of the North Pole. There were two people who claimed to have reached the North Pole, but actually they didn't reach the North Pole, really. That was somebody else. It was Ronald Amundsen, who was the first reaching the North Pole with an airship. Then another important name is Nansen. Yeah. And Nansen had the Fram ship, which is shown here, and he was the first going north and tried to freeze his ship and then drift with the sea ice through the Fram Strait. This is the Fram Strait. Yeah. Okay, and that's kind of an example of a very recent campaign. So we are still with history. I don't know if you have heard about the Mosaic Campaign. This campaign more or less tried the same as the Nansen expedition, but of course with much more modern instrumentation and facilities. Yeah, and just to show you a couple of slides here, this is the ship. This is the German Polarstern, an icebreaker, and but there were more icebreakers involved. It was a long-year drift experiment or drift expedition. A lot of nations were involved, institutes, a lot of people, so a huge thing, and a lot of equipment was taken there, and so on. So it was really a big effort. And just to show you what else, other than the ship, was placed there. So the ship was here, and it was fixed at ice floe. And on the ice floe, a lot of instrumentation was additionally installed. Mad City, for instance, here, towers and ground-based measurements, airborne measurements of helicopters, aircraft, measurements below the sea ice, Ocean City here, and Balloon Town. So balloons were launched and so on. So you see, the world has changed within 200 years, of course, but people are still eager to go there and to take measurements. And I'm always somebody who says it's very important to have models, but if you don't have measurements, then you cannot really work. It's always this combination between models and measurements that brings new results. Okay, so that brings me to the third point. The climate changes which are occurring and which we can observe. I would like to show you some observations that show what's going on in the Arctic, and it's really dramatic what's going on. What I will show you a little bit is the Arctic sea ice that changes, continental ice and glaciers, snow cover and permafrost. All these points which are listed here, I will show you some results in a minute. Let's start with the Arctic sea ice. And now I'm not sure if this video works. It might be that this video doesn't work. I had a video here, Stift, text, well, that won't, I'm sorry. I had a, yeah, that's a pity. That doesn't work because it would have shown how the sea ice cover here, that's the sea ice cover in September, this is Greenland, how it changes within the last 50 or so years. And it shrinks quite significantly. I'm sorry that this doesn't work, but you have here the link where you can download the video afterwards. In the end, what comes out is, for instance, we had two kind of maximum or minimum sea ice covers in 2012 and 2007. And you see that here, the red or the pink here, the pink line, this is the sea ice cover over a 30-year period. And the white one is the sea ice cover in September 2012, or in September 2007. And you see that this actual sea ice cover is much, much less compared to the 30-year average. So the sea ice cover has dramatically shrinked. That doesn't only hold for September, it also holds for January or for the winter, and that's what you can see here in this annual course. So here you have the year, January to December, and you see the annual cause of the sea ice concentration or the sea ice extent. The dashed curve is an average over a number of years, 50 years or so, and then you see here different lines which show certain years, and here are the last 10 years or so. They are plotted here. Right now, at the moment, we are here. So this red curve is for this year. And what you see is that all over the year, the measurements in the last 10 years, they were all below this average. Yeah, so that's a clear indication that's shrinking. Of course, the shrinkage is more in late summer here, where the minimum of the sea ice concentration is observed. But it's also obvious in winter, not that dramatic, but also you can see it there. So it's very inhomogeneous, this freezing and this decrease of the sea ice. What you can see here is the sea ice fraction and the trend of the sea ice fraction. So the blue one here is the sea ice fraction decreases, yeah, and the red is it increases sea ice fraction. So what you see is really in the central Arctic, of course, there's always sea ice, even in summer. But at the edges, you have large areas where you have a strong negative trend, but you also have a positive trend here at some areas, yeah, and that makes it so complicated. It's always very inhomogeneous. So, and in addition to that, the Arctic sea ice becomes younger and also thinner. Not only the coverage decreases, but also the thickness and the age changes. And for this purpose, have a look at this slide here. This compares March 1985 and March 2015. And the red one here, this one, is the 5 years and older sea ice. And you see that this has more or less, it hasn't changed dramatically, but what has changed is the 3 to 4 years old ice. That's the yellow one. It's much less here. Here it's much more for 3 to 4 year ice. And the area where the sea ice is 1 year old, less than 1 year old, so that means it's 1 year old sea ice, it is the blue one that has dramatically increased. Yeah, it's also thinner. Here are some numbers. 1980, an average over the whole Arctic was above 3 meters. Now it's much less. Yeah, and also the that holds for the winter and also for October, November when the refreezing starts. So dramatic changes occurring. Also, the Greenland continental ice melts. Greenland is the largest source of drinking water. So there's a lot of sea ice, a lot of ice, and that makes a big difference. And what you see here is the black curve is the decrease of the mass. That's here the Greenland mass change, the mass change. So it changes by quite a big number. So the trend is very clear. The sea ice mass is strongly decreasing. Here's the equivalent water height. That's the colors. Again, you see much change is going on over Greenland. Yeah. Greenland is very, very important also for the sea level. Glaciers retreat also in the Arctic, and these are just some examples of the same glacier, which was here in 1996. Then this is in 2008. So the red one is the former source, and here now it's 2 kilometers. It has retreated 2 kilometers within 20 years. Yeah, very dramatic. The snow cover. Another point. Here you see time series of 50 years or so. April, May, June of the snow cover extent. Yeah, so the coverage of snow cover. And you see that for North America, for Eurasia. But again, the trend is clear here. In particular in June, the snow cover decreases quite heavily. Yeah, another change or another signature of the changing Arctic. Permafrost thaws, also very, very dangerous. You can see that here. That's in, I think it's in Siberia. Yeah, here in Siberia, it changes. I mean, you see here there are dramatic effects of this change as well. Now, one of the most obvious signs besides the sea ice is the near surface air temperature. Yeah, that is on the rise. And you can see that clearly here. You have a time series here on the x-axis, and you have the geographic latitude here. So this is a global map, Antarctica, equator, and Arctic, you can see here. And the color here indicates the anomaly of the near surface winter temperature. So we have the winter temperatures, and we look at the near surface air temperature, and we look at anomaly compared to a 30-year average. I don't remember exactly what the average was. Yeah? Red means you have a warming compared to the average. Blue means we have a cooling. Yeah, and it's quite clear. First of all, you see a lot of red here. That's the global warming here. Yeah. However, in the Arctic, which is here, within the last 20 years or so, you have a much higher warming. The red is much darker here compared to the rest of the globe. That's what's often called Arctic amplification. Although I rather say that Arctic amplification is a multitude of processes that is very sensitive processes which are amplified in the Arctic. It's not just the temperature, but this is a very obvious sign. If you average that over the Arctic and compare it to the mid-latitudes, the tropics, and the global average, then again you have this time series here. You see that the Arctic stands out. Yeah, this is the Arctic here, and these are the curves for the tropics, mid-latitudes, and global. And you clearly see that within the last 20 years, kind of this diverged. So the Arctic accelerated in its warming compared to the global warming. Yeah. Again, that's very inhomogeneous. So here you see the temperature tendency over the Arctic Ocean. And again, you see what we have seen before for the sea ice as well. You see that there are spots, hot spots here in the vicinity of Spitsbergen, for instance, is a hot spot where the Arctic temperature additionally increases compared to the rest of the Arctic. Yeah, so that's why you have big problems, of course, in climate models to kind of represent that in the models. Yeah, and as a result, but not only as a result of atmospheric processes, but there are also oceanic processes. What happens is that the sea surface temperatures, it's not the air temperature, but the sea surface temperature rises as well, and that is related to a fact or a process which is called the Atlantification of the Arctic Ocean. Look here at the Arctic Ocean. The white is the sea ice, but you see here also again the sea surface temperature anomaly. Red means the sea surface temperature has warmed, so by 2 Kelvin here, for instance, yeah. And blue is it has cooled. And again, you see there are spots where it cools, but in general, it mostly warms. And if you look at a little more in detail at different places here, from Chukchi, Baffin, and Barents Seas, and you can plot time series here for the 3 places, Chukchi, Barents, and Baffin Bay, you see an increasing trend also in the sea surface temperature. Yeah, that's not all. The sea surface temperature also determines the biological production within the upper ocean layer. So that's called the primary production. And here you see if there's more radiation, radiation that can penetrate into the ocean because there's less ice, then this production increases. And here you see the trends in annual primary production. And again, yellow and red means it's increasing. Green means it's slightly decreasing, but most of the Arctic is increasing. And that's what's called the greening of the Arctic. Yeah. And sea level, it rises. And there are certain indications for that. If you look at measurements here, from different sources, again, this is from 1900 until today, you see sea level rises, and there's some acceleration behind. Before it was 0.6 millimeter per year, now it's 4.4 millimeter per year. And there are several effects going on here. They are distinguished also in this graph here. It's not only, well, the first point is that you have thermal expansion. Yeah, thermal expansion. If the ocean gets warmer, it expands, and that's quite some significant proportion here. But the glaciers, which I've shown, the Greenland itself, which is decreasing, the sea ice concentration, which is melting, Antarctica, and other sources, they also contribute. And these are now predictions or projections until 2100. And the projection is that in the worst case, these are these different scenarios from ICCP. In the worst case, we can have 0.6 meters increase in sea level rise. All right, so these are the facts. Now the question is, why does this happen? Why is the Arctic climate system changing so fast, and why it's changing faster than the rest of the globe? And altogether, there is a lot of different processes which are working. And we from AC3, from this project, we focus on atmospheric oceanic interactions. And for this purpose, we have had a look at intertwined feedback processes in order to try to explain these effects in the Arctic, these changes. And I would like to present you a simplified scheme that includes processes and feedback mechanisms within the Arctic climate system, which contribute to explain why the Arctic is changing so fast. And we just published that. So if you look at the Bulletin of American Meteorological Society, there's an early online release of a paper that we have published with results, first results of our project. And this scheme is part of that. So you can have a look at that if you like. So what happens? Well, first, we have global warming. No doubt about that. And that, of course, increases also the air temperature in the Arctic, the near surface air temperature. Sure, why not? Yeah. So what happens then is one process which is called the surface albedo effect. That's very well known already for more than 50 years. The warming near surface air temperature acts such that the sea ice and the snow is reduced, it's melting. Then the surface albedo gets less. Here the surface albedo of snow is very high, here white, and that of open ocean is very low. And that means the radiative heating of the ocean, mixed layer of the upper ocean area increases. That produces atmospheric energy fluxes that increase as well, and that increase the near surface air temperature. And this process is self-enforcing. So once you push the system, it's getting stronger and stronger. So that's one of the major effects within this Arctic amplification. However, that's not all. There are interactions with the ocean, with the cryosphere, ocean, and the atmosphere interactions, and also with the biochemistry. For instance, the biochemistry can change the surface albedo. If you have more algae, for instance, can change the surface albedo and then feeds into this other cycle. Or the radiative heating of the ocean, it changes, of course, the biochemistry. So you have a small feedback process here in itself, and so on. So there are several processes which you have to consider. That's not all. Then you have some atmospheric components. They are linked to these cryosphere ocean atmosphere interactions, but they are also linked to the warming ocean and also to the atmospheric heat fluxes. Those processes are related to trace gases, aerosol particles, water vapor. Water vapor is also trace gas, but nevertheless, clouds and precipitation, atmospheric lapse rate. These are processes which are interlinked with those other things. And on top of that, we also have atmospheric circulation and meridional transport processes. That's something which determines also the linkage between the Arctic climate changes and the mid-latitudes, for instance. There is this idea that if the Arctic is warming faster than the rest of the world, then the gradient, the temperature gradient between the Arctic and the mid-latitude decreases. That means that the west wind circulation is weakened. And that means that you have even more undulations and Rossby waves. And that these increased Rossby waves, if the amplitude increases and the stationarity increases, then it brings in cold air from the Arctic into the lower latitudes and also transports warm air from the mid-latitudes into the Arctic. And that could enforce the Arctic amplification. So there's a lot of room and a lot of processes within this scheme. And as I mentioned, it's a simplified scheme. Yeah, but this is more or less the basis for our project. So, and here, because I don't have too much time, let me have a look. I still have 10, 15 minutes, I hope. That's why I would like to concentrate on just one error here in this thing and go a little more deeper. That means the interaction between clouds and the atmospheric energy flux. I would like to dwell on that a little bit more, okay? All right, so that means what I'm doing now is have a look at the radiative energy budget below clouds. So because we want to see how clouds play in this scheme, how clouds, do they increase the Arctic amplification? Do they decrease the Arctic amplification? That's the question. Yeah. Okay. So let's first look at the terrestrial spectral range. So we have the solar radiation, but we also have terrestrial radiation. Solar radiation, the photons come from the sun. Terrestrial radiation, the photons are emitted from the atmosphere or from the surface. That's why it's easy to distinguish the two. Yeah. So let's focus on the terrestrial for the moment. And let's say, okay, we have measurements at the fixed location, at this measurement station, and over highly reflecting surface, sea ice or snow. So what then happens is that if you look at the frequency distribution of the net irradiance, so that's the net irradiance here, that's the energy budget below the cloud. Yeah, and the net irradiance is downward minus upward. If downward is larger than what is going upward, then you have a gain in energy, yeah, a warming. If that's not the case, then you have a cooling by the clouds. And what you see, if you look at the frequency distribution of measurements at a fixed location, and you see you have two modes here. One around 0, so it means downward is equal to upward, and the other one with negative values, where the surface is cooled. And these two things belong to cloudy and cloud-free cases. Cloudy, if the surface temperature and the cloud base temperature is not too large, if the difference is not too large, then you end up with more or less a net effect of 0. Yeah. However, in cloud-free case, then you have a cooling because the downward is much less than what is emitted by the surface. Yeah, that's why you get negative cases. All right, that was for a fixed location and over a longer time period. Now we wanted to also see what the surface changes here in this regard. And that's why we were flying with an aircraft below clouds, over sea ice, and also over open ocean. And we collected these data, downward irradiance and upward, and the difference gives the net irradiance. So we collected that for different situations and plotted them in kind of a 2D plot. This is the surface albedo, and this is the net irradiance on the y-axis. Yeah, and the colors here is the number of occurrence. So that's the frequency, how often we have measured such values. Yeah, we collected tons of data and put them all into one pot. And what you see again for the terrestrial is that you have this mode structure here as well. So you see here a cloudy mode and the cloud-free mode. That was the same what we see earlier. Now it's two-dimensional, but in the previous plot we had only a high surface albedo. Yeah, so we were more or less here in this area, and we have seen the cloudy mode around 0 and the cloud-free mode around -40, -50, 60 something. Yeah, but in addition now, because we were also flying over open ocean, where the surface albedo is low, we have two more modes here. Again, cloud-free and cloudy. So we have such a typical 4-mode structure. And we did that for a campaign in May, June 2017. We have further campaigns. Here's another example. That's for a more March to April, so that's earlier in the year. And again, we have these modes here, 4 modes, but they are kind of shifted. Yeah, so here they are more or less the same, at the same level here, or at least it was not that strong shifted. Here they are more strongly shifted, and that has to do with different synoptic situations with regard to the clouds. That means the cloud base temperature is very important. If that is that was different here in rather winter. This is already early summer. And also the vertical profile of the thermodynamic properties that determines the cloud-free mode mostly. So I could spend 10 minutes now explaining exactly why these differences occur. I just want to make the point, you need to be careful and have to look at different situations, and then you can interpret that quite well. It's not a static picture, but nevertheless, these four modes, they are very systematic and they are frequently occurring. So now, if you want to really look at the cloud effect, then you need to derive something which is called the cloud radiative effect. And that's now the net irradiance in cloudy minus the net irradiance in cloud-free conditions. So that isolates now the cloud effect, because we want to know, do clouds warm or do they don't they warm, or do they cool? And if you do that and plot a similar pattern, then you come up, you have here one mode, which is over sea ice, so high surface albedo. And that means the message is over sea ice, clouds mostly warm, whereas over open ocean, the clouds mostly cool. So clouds warm surface, clouds cool surface. So the surface is very important. Not only the surface is important, also the vertical profile of the thermodynamic parameters is important, and the cloud base and surface temperatures. All right, so now let's have a look at the sea ice mode only. And our objective now is to look if the common models can represent this sea ice mode, because you cannot compare measurements and simulations point by point, but you can do it in a statistic way. If the measurements, if the simulations are able to represent this structure, then that's a good sign. So let's have a look at how that works. And for our purpose, we have used the ICANN, that's the operational model of the German Weather Service. And we have nested the ICANN here in such a smaller area. And we were flying here in this within this area and have collected data there. And then we have operated the model. And then we were flying through the model, artificially, of course, and collected at the points where we have taken measurements, there we have also collected these simulations. And our hope was that we can reproduce the structure which we have measured. How did that work? Sorry. This is now, as I said, it's just the cloud mode over sea ice. Over sea ice, we just look at the cloud mode over sea ice. And what we find for the terrestrial spectral range is red is the measurement and blue is the model. Well, it kind of agrees quite well, I would say. Yeah, you cannot really complain here. You can't get much better. So the mode is well represented. This is the cloud mode over sea ice by both the measurements and the simulation. That's fine. However, if now look at the solar spectral range, then you have a problem. Yeah, the ICANN, the model is the blue one. It's significantly larger compared to the red one, which is the measurement. We'll talk about the reasons for that in a second. If you put both together, solar plus terrestrial, then of course you still have this problem from the solar. So the major source here of this discrepancy here between the simulations blue and red, is the measurements, is the solar part. So now we tried to dig deeper and ask why, what's wrong with the model. Yeah, and the suspicion is that the optical thickness is too low. Yeah, and that's why we have too much solar radiation reaching the ground. And that means the downward is larger compared to the measurements compared to the upward. Yeah. So okay, the optical thickness could be tau is determined by the extinction and the thickness of the cloud, for instance. Yeah. So we checked the cloud thickness. Is that well represented by the model? Yes, kind of. So that was not the reason. However, the extinction, that's the second option, which could be wrong, is a function of the number of the droplets and the liquid water content of the droplets. So we checked the measurements here as well, because we had measurements from the aircraft of liquid water content droplet number concentration. And what we've seen that actually, indeed, there are problems. So ICANN and A-Cloud, they don't agree here quite well. That holds for the liquid water content, but also for the number drop concentrations. And if you look at the size distribution, you'll see that too few small droplets are represented in the model. The measurements show much more low droplets, and vice versa for the larger droplets. That's the size distribution. So that means we can state the following. We can say, okay, it seems that the clouds are optically too thin in the model, and that the model produces too few small droplets. What's the reason? Well, one issue seems to be that the droplet accumulation in the model is not well represented. So what is used is a grid scale average of the vertical velocity. And of course, what is not used and what is not implemented in the model are fine scale small fluctuations of the vertical velocity. And those vertical velocity fluctuations, which are averaged out in the model, they bring activation of droplets which are not considered. And that's why the small droplets seem to be missed. Okay, and the corresponding action is that we try to modify the droplet activation scheme in order to consider subgrid scale vertical motion fluctuations, and rather than average and a Gaussian distribution was used here. So the result is that we got some improvement, not 100%, but it worked. And that's the way we think you can try to improve models, or also validate measurements. Measurements are also not always true. Okay, and that's my last slide now. I hope I didn't exceed too much, but I don't think so. 15 minutes already? Okay. So, summary. And I would like to answer this question, how field observation can help to constrain the models. That's kind of what I want to share. First of all, the Arctic is exciting. It's challenging. It's a true hotspot of the globe. And it's nice to go there because we can really measure something there, which can be interpreted. And of course, you can do that in other parts of the world too. But in the Arctic, you have very dramatic changes, which should easily be more to be measured. And those changes, they are not restricted to the Arctic. They can really affect the entire globe. In terms of in terms of this question here, how can field observations help to constrain models? I would say that data from targeted field observations, they are good to compare model output, to identify and fix model issues, introduce and subscribe subscale processes, and provide parameterizations. The models are good to project the future. Otherwise, we cannot disentangle all these different processes. And also to investigate teleconnections. And last but not least, my last statement is a smart combination between models and observations is key. And with this, I would like to finish. I would open the round of discussion. And as I said, I hope I didn't exceed my limit too much. Thank you for your attention.
Yeah, thank you, Professor Manfred. Now, the webinar is open for question, answer, and discussion. So the participant can raise the question.
Yeah, I just have one small, it's not a question, it's more like a clarification. So one of the slides that you showed was when you actually showed the net radiation in a cloud-free and in a cloudy sort of situation. The cloud-free had more negative net radiation, minus 40 watts per meter squared. So in the normal situation over Arctic, would would it be like, would it be more common to have a cloudy environment or a cloud-free environment?
Both states are common in the Arctic. And that's why these two modes come out so clearly. Yeah,
okay.
There's little in between, but these two states are very common. Of course, clouds may and will change in the future. But that's another topic. I think that's not what you're asking for. I mean, the suspicion is that the clouds will increase because if you have more open ocean, more heat from below, then it could be expected that you have more clouds in a warmer Arctic. But there are also other processes. Yeah.
So the changing climate would possibly ensure that we move to a situation where more clouds are seen or observed. Am I correct?
Yes, that's the suspicion, and that would mean if you have more open ocean, because over the open ocean you have a rather a cooling effect. Yeah, that's what you see here. Over the open ocean, you have a rather cooling. That's just the terrestrial. Yeah, but over the ocean, clouds tend to cool. Over the sea ice, they rather tend to warm. In particular, of course, during polar night, of course, because then there's no solar. Yeah, so that could mean that in a warmer Arctic in the future, this warming could be kind of reduced, could be kind of reduced by the clouds, which are more frequent over the ocean. And there's more ocean, and we should not forget that, because mostly people say, okay, clouds, they warm in the Arctic. And that's true, but they only warm over the sea ice. If the sea ice is gone, then we have clouds which cool.
Oh, okay. Okay, thank you.
Thank you for the question.
Yeah, Tejas.
Hello, Professor Wendisch. Thank you for this insightful talk. I wanted to know that we find this polar amplification mainly towards Arctic and not towards Antarctic. Is it because of the continental and oceanic asymmetries that we have on Earth, or does it have some other major explanation for it?
Yes, a very valid question. The point is that between the North Pole and the South Pole, there are, as you already said, there are different conditions. The Arctic is more or less a large ocean that is covered with sea ice. Antarctic is a large, huge continent, which is also covered by ice, but by land ice. The Antarctic is more or less, the ice is until 2,000 meters thick, vertically. And for instance, these processes which I mentioned, let me go back here. So these processes here, they work in the Arctic. Here, for instance, this process, it works in the Arctic because we have an Arctic Ocean. Yeah, over Antarctica, even if the sea ice melts, the surface albedo doesn't change because you don't have an open ocean below. Yeah, right. It works at the edges of the continent, but over Antarctica, this process cannot work. Yeah, you have 2,000 meter thick ice there. You can melt it, but the surface albedo won't change. So that's one thing. But there's also the dynamics because of this huge block of ice in Antarctica. The circulation is stronger. The Arctic Circle, the Arctic circulation is more disrupted because it's more inhomogeneous, and that's why you have from time to time you have these atmospheric meridional transports here, which you don't have in Antarctica. Yeah, so most of these processes here, they simply don't work in Antarctica, and that's my answer to your question. Are you satisfied with that?
Yes, Professor Wendisch. Thank you so much. If I may, I also was curious about any variation in cloud fraction or cloud cover trends over the years for the Arctic. If you have any thing to say about it.
Yes, there are some publications, but to be honest, I don't actually remember if there are clear trends. I mean, in our project here, in this AC3 project, there's one sub-project which looks dedicated as at the trends of aerosol particles and of clouds in the Arctic. And the result is kind of, I would say, preliminary. So don't refer to me in this regard. But for the aerosol, there's a decreasing trend, which makes sense, kind of, yeah, because pollutions are decreasing. For clouds, the trend is that the liquid water cloud optical thickness increases and the ice cloud optical thickness decreases. That means that the reflectivity by the clouds increases, sorry. Yeah. So that's what we found, but I would say be a little bit cautious with that. But it looks like there are trends, but it's very, very tricky. These results come from satellite measurements, and doing satellite measurements over sea ice is a huge challenge. And that's why we are still working on that. But in the meantime, a preliminary result is, coming back to your question with the clouds, is that there seemed to be a trend in the liquid clouds. They tend to increase, the ice clouds tend to decrease, and altogether the reflectivity at the top of the atmosphere doesn't change.
Thank you so much, Professor.
Mm-hmm.
Yeah, thank you. So any other questions? So if there is no question, then let us thank Professor Manfred for his valuable and very important talk. So on behalf of all participants and as the community, I take this opportunity to thank you very much for your time and sparing time with us today. So I'll circulate your presentation to all our students, and if they have anything, I will definitely get back to you, sir.
Yes, I will replace the current version with the most latest version in 10 minutes or so. Please wait for that.
No, sure.
But then
sure.
you are free to distribute the link. Okay. And I would also like to thank you for inviting me. It's always I always enjoy to have a young audience and people listen to me. Thank you.
Yeah, thank you, because it was a very long-awaited talk. I think from last year we have been waiting for this, and finally we could make it. So we really want to thank you for that, and we'll definitely revert you back with our more questions and research aspects in your future related to Arctic. Yeah, because I also worked as part of my postdoctoral project in the Arctic region, mainly Barrow and Nelson, for black carbon measurement. So it would be really nice. I'll definitely go through your presentation in detail and we'll get back to you.
Yeah.
Thank you. So with that, we will end of this webinar, and I also thanks all the participants for participating this webinar. So thank you, everyone. Thank you, Professor Manfred.
Yeah, thanks, and best regards from Germany.
Thank you very much. Thank you.